Hello everyone, welcome to this lecture. So the plan for this lecture is as follows. In this lecture we will introduce the basic terminologies related to graph theory. We will discuss about different types of graphs and we will also discuss about Euler's theorem. So what is a graph? It is a collection of two sets, a set of vertices and a set of edges. So the set of vertices is denoted by the set V and it is a non-empty set of vertices also called as nodes, and we have another set of edges denoted by this notation capital E which have edges of the form Vi comma Vj where both Vi as well as Vj belongs to the vertex set, and this edge set could be empty. So what it means is that in a graph you can have a graph which has no edges, but the vertex set cannot be empty. The vertices are always there. You can't have a graph which is where the vertex set is empty as well as the edge set is empty. Okay. So we have two types of graphs, directed graphs and undirected graphs. When I say directed graphs, then pictorially you can imagine that in directed graph the edges have directions associated with it. That means we have the notion of the starting point of an edge and the ending point of an edge. And in terms of set theoretic notations, we can say that a directed graph is a graph where the edges are ordered pairs. And as soon as I say that the edges are ordered pairs, that means it matters whether the starting endpoint is Vi or the starting endpoint is Vj if you're talking about an edge Vi comma Vj, right? So for instance, if I consider this directed graph, then the edges that we have here are the ordered pairs v1 comma v2 because the starting point of this edge is v1 and the end point is v2. We have, but that does not mean that in the graph we also have the edge from v2 to v1 because that edge is not there explicitly in this directed graph, right? Whereas if we consider undirected graphs, then the edges have no direction associated with them, which is equivalent to saying that the edges are unordered pairs. That means when I consider this edge from the vertex v1 to vertex v2, it can be also considered as an edge from v2 to v1. In that sense, the edges are here bidirectional. Okay, so let us now define what we call as a simple graph, and this definition is applicable both for the directed graph as well as undirected graph. So a simple graph is a graph which has no self loops. Okay, and there can be at most one edge between any two nodes. Okay, so if I consider this undirected graph, then this is not a simple graph because between the nodes v1 and v3 you have two edges, this edge as well as this edge, okay, which is not allowed as per the definition of an undirected simple graph. But if I consider this directed graph, then this is a simple directed graph because even though you have two edges involving the nodes v1 and v3, this is one of the edges and this is another edge, they are different directed edges because the ordered pair v1 comma v3 will be different from the ordered pair v3 comma v1. So this is an example of a directed simple graph. Okay. So now let's introduce some terminologies related to undirected graphs. So if you are given an undirected graph, then a pair of vertices u comma v are called adjacent or neighbors of each other if the edge u comma v belong to my edge set. Okay, that means if u and v are the endpoints of an edge, then in an undirected graph, then we call the vertices u and v to be adjacent or neighbors. Okay. Here v could be e, that's allowed. V could be u, that's allowed. That means if I have a self loop, then the vertex v will be called adjacent to itself, right? Then if we are given an edge small e, then we will say that it is incident with the nodes u comma v if u and v are the endpoints of the edge. So for instance, if I consider this edge small e, then v1 and v2 are incident with respect to this edge because they are the endpoints of this edge E, and so on. Now let us define next what we call as the degree of a vertex small b. So again, I am giving the definition with respect to undirected graph, but the definition can be extended or generalized for directed graphs as well. Okay, so what is the degree of a vertex? The degree of a vertex is the number of edges incident with V, or in the simpler language, the number of edges which have small v as one of its endpoint. Okay, and the definition has a special case if we have a self loop uh, incident with the vertex small v. So if there is a self loop incident with the vertex small v, then that self loop uh, is counted as contributing 2 to the degree of the vertex small v. Okay. So for instance, if I take this undirected graph, then the degree of the vertex v1, let us find out what's the degree. So how many edges are there incident with the vertex v1. So this is one of the edges, this is another edge, okay, to the 2 edge, and now we have this edge again incident with v1, so total 3. Whereas if I consider the degree of the vertex v3, then we have this edge, this edge, this edge, and we have a self loop. The self loop will be counted twice while counting the degree of the vertex v3. So total the degree of the vertex v3 will be 5, and so on. Okay. So this degree of a vertex, the definition is with respect to the undirected graph. The undirected graph need not be simple. In fact, in this particular example, between the vertex v3 and v1, we have 2 edges, and both of them are counted while counting the finding the degree of the vertex v3. Next, we state a very fundamental fact about an undirected graph. This is also called as the handshaking theorem. So if you are given an undirected graph, it may be simple, it may not be simple, it's just an undirected graph, and say the graph has m number of edges, then what the theorem basically says is that if you sum the degrees of all the vertices in the graph, then it will be twice the number of edges, always. Okay. So you can verify this with respect to this example graph. You take the summation of the degree of the vertex v1, the degree of the vertex v2, and the degree of the vertex v3. It will be equal to twice the number of edges in the graph. So so you have 1, 2, 3, 4, 5, 6, and 7 edge. So 2 times 7 is 14, and you can verify that. So degree of v1 is 3, and degree of v2 is 2, 4, 5, 6. Degree of v2 is 6, and degree of v3 is 1, 2, 3, and 5. Okay. So let us prove this. The statement is true for any undirected graph. So consider any arbitrary edge in your undirected graph, u comma v. It may be a self loop, that means v could be same as u, or it may not be a self loop. And let us try to find out that what will be the overall contribution of this edge when we are summing up the degrees of all the vertices in the graph. So the claim is that the contribution of this edge will be 2 to the overall summation of degrees of all the vertices, because this edge will be contributing 1 when we will taking the degree of the vertex u, and it will be again contributing 1 when we are taking the degree of vertex v. And if u is same as v, then as per the definition of the degree, the self loop will be counted twice, right? Because u will be same as v. So that's why in the expression, when we are summing up the degrees of all the vertices in the graph, the contribution of the edge u comma v will be 2, and hence it's easy to see that the summation of the degrees of all the vertices will be twice the number of edges in the graph. Okay. So based on this fundamental fact, we can derive another conclusion about any undirected graph, and this conclusion is often called as the Euler's theorem. So what it says is the following: if you have okay, so what this theorem basically says, it says that you take any undirected graph, then the number of vertices of odd degree will be always even. That means you will either have zero number of vertices of odd degrees, or two vertices of odd degrees, or four vertices of odd degree, or so on. That means it won't be the case that the number of vertices of odd degree is odd. And for that, for deriving this conclusion, we will use the previous fact, namely the summation of the degrees of all the vertices in the graph is twice the number of edges. And the proof is very simple. So let V be the set of vertices in your undirected graph. The set V can be divided into two disjoint sets. The set V odd, which is the set of all vertices which have odd degrees, and the set V even, which is the set of all vertices which have even degrees. And it's easy to see that the intersection of these two sets will be empty, because you can't have a vertex in a graph which has both odd degree as well as even degree. A vertex will have either odd degree or even degree, and hence it will belong either to the set V odd or to the set V even. So these two sets constitute a partition of your set of vertices V. Now what I can say is that if I take the summation of the degrees of all the vertices in the graph, then that is equivalent to the summation of the following two quantities. You take all the vertices in the set V odd, namely all the vertices which have odd degrees, and take the summation of the degrees of the respective vertices in the set V odd. And you take all the vertices in the set V even, namely all the vertices which have even degrees, and sum of their degrees. And if you sum these two quantities, that will give you the summation of the degrees of all the vertices in the graph. Now I know that the left hand side of this equality is even, because as per the above theorem, the left hand side is 2 times the number of edges. The number of edges could be odd, it could be even, but 2 times that number of edges will be an even quantity. So I know that the left hand side is an even quantity. And I also know that if I sum up the degrees of all the vertices which have even degrees, then that is also an even quantity. The number of vertices of even degree, it could be odd, it could be even, it doesn't matter. But since I am adding several quantities, each of which is an even quantity, the overall summation will be even. From that, I can conclude the following, that I can conclude that if I sum up the degrees of all the vertices in the set V odd, that also will be even, because if that is not the case, then you can't have the difference of two even quantities, because that is simply coming from the fact that the summation of the degrees of all the vertices in the set V odd is the difference of two even quantities, and the difference of two even quantities will be even. So what is the conclusion that we have drawn till now? We have concluded that if I take the summation of degrees of all the vertices in the set V odd, then that is an even quantity. And that is possible only when the number of entities in the set V odd is even, right? So because you are summing up several odd quantities, and the summation of those odd quantities is even, that is given to you, that is possible only when the number of quantities that you have added is even. Okay? So that's a fundamental fact about any undirected graph, irrespective of whether it is a simple graph or a non-simple, or whether it's not a simple graph. Okay. Now let us define some special types of undirected graphs. So the first special type of undirected graph is a complete graph. And the property of this graph is that you have exactly one edge between each pair of distinct vertices. And since this is a simple graph, okay, And our property is that you can't have more than one edge between every pair of distinct vertices. Automatically, we have here the restriction that you can't have a self loop, because if you have a self loop, then that self loop will be uh, violating the definition here. So the requirement here is that you take the vertices, all the vertices between every pair of distinct vertices, you will have exactly one edge. You don't have the option of 0 or 1. Exactly one edge should be there between every pair of distinct vertices. And if n is the number of nodes in a complete graph, then we use this notation k sub n to denote a complete graph with n nodes. So these are the examples, some of the examples of complete graphs with various values of n. The complete graph with 7 nodes is this, complete graph with 4 nodes is this, complete graph with 12 nodes is this. Then another special type of simple undirected graph is a cycle graph denoted as Cn. Here the vertex set will be consisting of n nodes, and you will have edge set of the form of the following. You will have an edge between the vertex 1 and 2. You will have an edge between 2 and 3. You will have an edge between the n minus 1 vertex and vertex Vn. And then you will have an edge between the vertex Vn and V1. Now, since the graph is simple, okay, the cycle graph is defined only when the number of vertices is n is greater than equal to 3. Because if I try to define a cycle graph involving just two nodes, then as per the definition, the edge set will be the following. You have an edge between uh, 1 and 2, and again you have an edge between 2 to 1. Okay, that will be the definition of the edge set as per this general definition, but that will violate the property that it is a simple graph. So that's why n is greater than equal to 3, and then only we can define a cycle graph. Well, you can't say that why can't I take this to be a cycle graph, namely a graph where I have just an edge between 1 and 2, because the interpretation of the cycle here is the following. The interpretation of the cycle is that once you go to the nth vertex, you have an edge from the nth vertex back to the first vertex. Okay, so without violating the requirement that your graph is a simple graph, this is possible only when n is greater than equal to 3. So if I consider a cycle graph with 3 nodes, then that will be something like this. You have V1, V2, V2, V3, and then you have an edge back from 3 to 1. Okay. Then there is another special simple undirected graph called as the wheel graph. So it is slightly different from the cycle graph. So what you do is you take a cycle graph involving n minus 1 nodes, and then you add a central vertex, which is the nth vertex. And the central vertex is now uh, we add an edge involving the central vertex and all the vertices in your cycle graph C of n minus 1. Okay, so for instance, if I want to form W4, then I take the cycle graph involving 3 nodes, add the fourth vertex V4, and add an edge from this fourth vertex to every other existing vertex in the cycle graph. We also have another special simple undirected graph called as the n cube or the hypercube, denoted by this notation q of n. So this graph will have 2 to the power n nodes, where each node represents a possible n bit string. So remember that the number of bit strings of length n is 2 to the power n. So each string is represented by a node in this hypercube graph, and you have an edge between the ith vertex and the jth vertex if the bit strings represented by the ith vertex and the jth vertex differ in exactly one bit position. Otherwise, the edge is not there between the ith vertex and the jth vertex. So for instance, if I take the graph Q1, then I can have only two bit strings of length 1. the bit string 0 and the bit string 1, and they differ in exactly 1 bit position, so the edge will be there. If I want to form the graph Q2, the way I do it is as follows. So there will be this will be the graph Q2, okay, because you will have 4 bit strings of length 2, and you can see that this edge is there because the binary string 1 0 differs with the string 0 0 in exactly 1 bit position, namely the first bit position. You don't have an edge between the bit string or the vertex 1 representing the bit string 1 0 and the vertex representing the bit string 0 1 because these 2 bit strings differ in more than 1 position. So let me go back and try to understand that what exactly is the relationship between Q2 and Q1. How exactly I can interpret Q2 or relate Q2 with the graph Q1. So the way I can construct the graph Q2 is as follows. I take 2 copies of the graph Q1. This is your first copy and this is the second copy. In the first copy, I add the bit 1 at the beginning of all the nodes or all the bit strings uh, represented by the nodes in the copy of Q1, right? So the copy of Q1 that I would have taken is the following. I would have taken the vertex representing the bit string 0, the vertex representing the vertex bit string 1. What I'm saying is you add a 1 at the beginning of these bit strings. You take the second copy of Q1 and you add a 0 at the beginning of all the strings represented by the nodes in this copy of Q1. And now you add the required edges depending upon the bit strings differ in exactly 1 bit position or not. Okay. In the same way, if I want to get if I want to define or get the graph Q3, what I do the following. I take 2 copies of Q2, 1 copy of Q2, another copy of Q2, and I extend the length of the bit strings of the nodes by adding 1 at the beginning of all the strings in the first copy of Q2, and I add 0 at the beginning of all the bit strings in the second copy of the Q2, and then I add the required edges depending upon whether the 2 vertices differ in exactly 1 bit position, right? So that's the definition of our Q1 graph. Now let us next define what we call as bipartite graphs. So if you are given a simple graph, okay, then the graph is called bipartite if we can find out 2 vertex sets V1 and V2 such that the following hold. The vertex sets V1 and V2 should constitute a partition of your vertex set. That means the union of V1 and V2 should give you back the original vertex set and there should not be any overlap or intersection between the vertex sets V1 and V2. And the second property that I need from this partition V1 comma V2 is the following. I need the following. You take any edge E in the graph with endpoints whose endpoints are Vi and Vj, then one of the endpoints should be in one of the subsets and the other endpoint should be in the other subset. So what it means is that you take any edge of the graph, it can't be the case that both its endpoints are in the same set, say V1 or in the set V2. One of the endpoints should be in V1, the other endpoint should be in V2. Okay. So for instance, if I take this graph, then this graph is not a bipartition graph. It's not a bipartite graph because I can't find the required V1 set and V2 set. This is because if I focus on this specific portion of the graph, namely this portion is the triangle graph. Okay. So if I call these as edges as E1, E2, and E3, and if I try to find out a candidate V1, V2 satisfying this condition, I can't do that. Say for instance, I include this red colored vertex in the set V1. So let me call these vertices as A, B, C. So suppose I include A in V1 As per my requirement, since the other endpoint of edge E1, namely the vertex V should be the other subset or other partition, uh, I should put the vertex B in the subset V2. That's fine. Now, what about the edge E2? The other endpoint of the edge E2 is C, so it can't go in the same set V2 because that will violate my requirement. So I can put C in the collection V1. But as soon as I put C in the collection V1, I see that I get a violation because I now have an edge, namely E3, where both the endpoints A and C are in the same collection V1, right? So that's why, irrespective of how you try to come up with your candidate V1 and V2, you can't find a partition V1, V2 for this graph satisfying this requirement. So that's why this graph is not a bipartite graph. But if I take this graph, then this graph is a bipartite graph. And what will be the partition set for the vertex set V? What you can do is you take all the blue colored vertices and put them in the collection V1, and you take all the red colored vertices and put them in the collection V2. And now you can see that you take any edge E in this graph, one of its endpoint will be in this V1 and the other endpoint will be in V2. It won't be the case that both its endpoints are either in V1 or in V2. So that's why this is an example of a bipartite graph. Now let's define next what we call as a complete bipartite graph. So it is a special type of bipartite graph. So first of all, it is a bipartite graph, namely it should be possible to come up with a partition of the vertex set, and that partition should have a special property. Now you take any edge in the graph, one of its endpoint should be in V1, other endpoint should be in V2. That comes from the definition of the bipartite graph, but this implication is now a bi implication. That means it is the case that you have an edge in the graph between each and every vertex in the set V1 and the set V2. Okay, so if you compare this by implication condition with the previous definition, in the previous definition, it might be possible that you have some vertices in V1 and some vertices in V2 such that between those vertices you don't have a edge in the graph. So for instance, if I take this graph, then this is a bipartite graph, but this is not a complete bipartite graph. Why it is not a complete bipartite graph? Because if, say, for instance, you take this vertex, it will be in one of the subsets given by your partition, and you take this blue colored node, this will be in the other subset in your partition, but you don't have an edge between these two vertices in the graph. Okay, so that's why this implication was there only in one direction. But in a complete bipartite graph, what I am saying is the implication should be a bi implication. Okay, so that's why this graph is not a bipartite graph, but this graph is a bipartite graph because you can put the vertices u1, u2, u3 in one subset, and you can put the other vertices, namely v1, v2, v3, v4 in the other subset, namely v2. And you can check now that you take any edge in the graph, one of its endpoint is in v1 and the other endpoint is in v2. So that shows the implication is true in one direction, and the implication is true in the other direction as well. You take any vertex in v1 and any vertex in v2, there exists an edge between those two vertices in your graph. Okay, so that's why this is a complete bipartite graph, and we use this notation k of m comma n to denote a complete bipartite graph where the cardinality of the two subsets in your partition are m and n respectively. Okay, so that brings me to the end of this lecture. These are the references used for today's lecture. So the basic concepts related to graph theory you can find in the Rosen book, but there's also this advanced or dedicated book for graph theory. So this is This book on graph theory is very nice. It covers both the basic concepts as well as advanced concepts. And if you are interested to explore graph theory, I encourage you to get a copy of this book. Okay. Thank you.